Have you ever stopped to think about the hidden forces that are just all around us, working in our world? Well, today we're going to dive into one of the most powerful ones, a super simple principle that lets a tiny little push move a mountain, or, at least a 2-ton car.
I mean, really think about that for a second. How on earth can a little push from your foot bring a massive, speeding chunk of metal to a complete stop? It feels like magic, right? But, spoiler alert, it is definitely not magic.
The secret is this absolutely brilliant principle of physics that's all about how pressure works in fluids. It's such an elegant idea, and it has totally reshaped the world of engineering and, as you're about to see, your everyday life.
So here's our game plan. First, we'll talk about this hidden force. Then we'll get into Pascal's powerful principle itself. After that, we'll check out hydraulics, these amazing force multipliers. Then we'll see where this pops up in daily life. And finally, we'll look at some weird stuff with pumps and siphons. Let's get into it.
Okay, let's start with the guy who figured all this out. We're talking about the brilliant 17th century physicist and mathematician Blaise Pascal. He's the one who uncovered this fundamental rule that explains exactly how pressure behaves in fluids.
So, here it is, the core idea. The two phrases you really got to remember are enclosed fluid, so it's trapped inside something, and transmitted undiminished. Now that second part is the real kicker. It means the pressure doesn't get weaker as it travels. It's like a perfect messenger, delivering that force instantly and equally everywhere.
The absolute best way to picture this is with a water balloon. Come on, you've done this. When you squeeze one part of it, the whole thing gets tight, right? You don't just see a bulge where your hand is. That's because the pressure you're applying is instantly sent everywhere inside, pushing out equally on every single inch of that balloon's skin.
Okay, so if pressure travels perfectly through a fluid, how do we actually use that? Well, this is where things get really, really cool. We can actually build systems that turn a tiny little push into an incredibly mighty lift. Welcome, my friends, to the world of hydraulics.
The trick is all in the design. Just imagine you push down with, say, 10 pounds of force on a little piston. That pressure travels, remember, undiminished, through the fluid over to a piston that's 10 times bigger. And what happens? You get a 100-pound lifting force on the other side. You've just multiplied your effort by 10. It's like physics-based leverage, and it's awesome.
And once you get this, you start seeing it absolutely everywhere. That hydraulic jack in the trunk of your car that lets you lift the whole car with just one hand? Yep, that's Pascal's principle. The brake system we were talking about earlier, same exact idea. From massive construction cranes to the chair at the barber shop, they all use this simple, powerful concept.
But hey, it's not all about giant, heavy machines. This very same principle is at work in much smaller things you might actually use every single day. Just take a simple syringe. When you push that plunger, you're putting pressure on the liquid that's trapped inside. That pressure gets sent equally and instantly everywhere, and it forces the liquid out through that tiny little needle. It's basically a perfect handheld hydraulic system. Okay, get ready for a classic mythbuster, the drinking straw. We all think we're sucking the drink up, but that's not what's happening. What you're actually doing is lowering the air pressure inside the straw. Meanwhile, the normal air pressure of the world is always pushing down on the surface of your drink. When the pressure inside the straw is lower, the outside pressure wins and literally pushes the liquid right up into your mouth. Crazy, right? And this doesn't just work for liquids, it works with gases too. Think about a bicycle pump. With every single push, you're squeezing air into a smaller space, which cranks up its pressure. As soon as the pressure inside the pump is higher than the pressure in your tire, the air rushes in. Simple, super effective, and it's all thanks to Pascal.
So now that we've got a handle on pressure, let's look at a couple of situations where it makes fluids do something that just looks impossible, like defying gravity.
Seriously, it really looks like it's breaking the laws of physics, doesn't it? If you've ever used a siphon to drain a fish tank or something, you've seen this bizarre effect. Water just seems to flow uphill and over the edge. But once again, it all comes down to pressure.
So here's the secret. It's really a battle of pressures. See, the weight of the water in that long downward part of the tube creates a low pressure spot at the very top of the arch. Now, the normal atmospheric pressure pushing down on the water in the higher tank is stronger, so it just pushes the water up and over the hump to fill that low pressure gap, and that gets the whole flow started. It's just high pressure pushing towards low pressure again.
This whole idea of pressure difference is exactly how we move water on a much bigger scale with pumps. Atmospheric pumps are basically like giant straws.
They use the air's natural pressure to help lift water, but there's a limit to how high they can go. For the really big jobs, we need mechanical pumps. Those things create their own intense pressure to force huge amounts of water wherever we need it.
So when you step back and look at the big picture, it's pretty incredible. All of these things that seem so different, a brake pedal, a syringe, a siphon, a giant construction crane, they're all powered by the same single elegant rule of physics that was figured out centuries ago. It just goes to show how one powerful idea can totally shape our world.
And that leaves us with one final thought to chew on. Now that you know the secret, a small effort creating a huge result by using a trapped fluid, what else are you going to spot in your world that's secretly a hydraulic machine? Start looking around. The answers might actually surprise you.